So our next speaker is Mark Rea, who is the Professor of Architecture and Cognitive Sciences at the Lighting Research Centre at Rensselaer Polytechnic Institute. And he's going to be talking on Where and What, Reframing the Vision Lighting Research Agenda. Please welcome Mark.
Yeah, of course. Good. Yeah. Is that fine? Everybody hear me? Well, I have to begin by saying it's an honor to be here. I've been involved with FSLL for a number of years. When I was in Canada, it was such a treat for me to come to these meetings because most people wore a tie. The men that were there was dominated by men, of course, and it was such a gentlemanly affair. If you'll excuse the sexism on that, but at the time it was mostly men. It always has had a high standard to me. It was always a pleasure to go because we had an attentive audience. And I always felt that it was a second home. So I appreciate very much the invitation to come back and say a little bit about some of the research that I think is foundational for lighting practice. Ian, in his introductory comments, and Mike also alluded to it, was the notion that the lighting research that we do really is a foundation for the lighting practice, the lighting standards that we have. But I would say we're not too far advanced from 1924 when it comes to standards. We are still recommending horizontal illuminance primarily on a function that was developed in 1924. Now, I consider that a remarkable achievement, but time has moved on and a lot of the other parallel research that's going on. So it's, to me, impressive that lighting is still using photopic illuminance when, if you look at it from a big picture, we're now seeing lighting affecting not only the visual senses that we have, but it also the non-visual effects. Now, I won't talk about the non-visual effects today, but the lessons are still the same. Are we ever going to come to grips with the non-visual? My point is we probably should think a little bit more deeply about something we're more comfortable in the visual domain. So when you think about light, you can break it down into amount, spectrum, distribution, timing, and duration. That's what the professional has the degrees of freedom that she can control to affect the visual system. Now, big picture, which I'll talk about the where and the what, is really visual system has two main threads. One deals with broadly what we call appearance, and the other is what we call visual performance. Now, it's interesting that what we have done in applications research, how does this space look, and can I see a black cat crossing the road? Those are topics that we've been very interested in. But fundamentally, there's a neurophysiological set of channels that actually deal with those two tasks separately. So even though you have the same image on the retina and you share the same photoreceptors, more or less, as an image is projected onto the retina, you have three basic channels, the P, K, and M channels. P for parvocellular, M for the M channel, and conocellular for the three wires, basically, that go to the first stop, the lateral geniculate nucleus. So already from the retina, we've stopped talking about photoreceptors, which has been sort of a central discussion. But now we need to think about how are those different channels affecting appearance and visual performance. They project to the primary visual cortex. They do image enhancement from the retina to the brain. And then it segregates, and so the temporal lobe is dealing primarily with what does it look like? What is it that I'm observing at this time? And that P and K channels are the primary dimensions for that. Where it is turns to be driven by the parietal lobe. Now each of those has different biophysical characteristics, and what applications research in lighting has done has been tweaking each of those, coming to some conclusions about how much light do you need to accomplish visual performance or whatever it happens to be. Now it turns out, and I'll move on from the neurophysiology a little bit, that the primary visual cortex is a two-way street. So part of the brain handles what, part of it where, then they come back together and give us a holistic view of what our environment is. So it's a constant projection forward and feedback that allows us to have a holistic view of what and where our visual environment is all about. Now, I think that the black curve is the photon, well, no, I'm sorry, that's V10, but it's more or less the achromatic visual spectral sensitivity that we use in all our light meters. And yet what we see is that depending upon whether we're going to tap visual performance or appearance, the bias towards V lambda or V10 lambda in this particular case is quite profound when you think about it. There's a lot of activity going on at short wavelengths, which as lighting professionals we kind of discount altogether. Now I want to point out that only one of those curves is actually a photoreceptor, and this is something I'd like for you to retain. We need to stop talking about photoreceptors, and now we begin to think about how channels of what and where are actually managed by the brain. Because I think there's a huge opportunity in applications research to take advantage of the neurophysiology that we understand to enhance societal benefits from lighting. And I think everybody in this room would very much like to embrace that. So I'm going to start talking about visual performance. This is the where things occur, and it probably helps to understand that this is generally speaking, not exclusively, but generally speaking off axis. And it's one of the things that's amazing to me is how, and I'll talk later about it, how we've discounted off-axis vision, and yet it's so critical to our ability to negotiate stairs or drive a car and so on. These represent the spectral sensitivities at different light levels. So you shift from a cone-dominated response, in particular L and M cones, and not S cones, and not intrinsically photoreceptive ganglion cells until we have a strictly rod-only vision. And so understanding how those transition is critically important because all of our roadway lighting deals in this mesopic level, somewhere between the rod and the cones. And depending on where you're looking, that spectral sensitivity can shift more towards the cone sensitivity or more towards the rod sensitivity. Let's see. We seem to have lost control of that, so let's move to this one and see if that helps. So we did some experiments, now going back to the history. What you have here is a half cylinder and, and a subject looks into this half cylinder, and what you're looking at is, maybe if I move that, what you're sorry. Can we turn that off? Yeah, I think so. Right, what you're doing is you're actually, no, it's not. All right. Sorry, I apologize. What your task, geez. Maybe you can hear me without this. Is that going to affect anything if we turn it off? Thank you. Is that better? Can you hear me? All right, good. Then let's dispense with that. All right, so the subject, you can see an eye here looking into a uniform field, and their task is simply to release a button as an object appears either in the fovea or 10 degrees off axis. So it's the same spectrum. And you're going to now change the total amount of light that you're going to see in that half cylinder. Okay. So geez. So on axis, what you see is a curve here as you change the background luminance of that half cylinder, and now you're flashing what would be metal halide or a high pressure sodium fit. It really doesn't matter on axis what the spectral power distribution is the source. It is a V lambda response, and that again is where we were in 1924. So here's another confirmation of the value of V lambda for detection. But now if you look at that same target now, metal halide, high pressure sodium off axis, what you see is this bifurcation of which we become less sensitive, relatively speaking, to high pressure sodium than we do to metal halide, as reflected by the shorter reaction times for metal halide. So being able to model that became the task we set for ourselves, and now that's the one that's eventually been adopted by the CIE. But basically you're looking from V10 lambda cone only to rod only that follows this surface. As you change the SP ratio, the scotopic to photopic ratio, what you see is high pressure sodium and LED on that surface. And this is the transition that the neurophysiology goes through as it changes from a rod to a cone and back again, in which you reach this flat period up there where your spectral sensitivity is determined by cones only. That helps us then in designing things like roadway lighting. What should we be doing off axis for visual perception? Now on axis, this is an experiment that we did many years ago when I was in Canada at the National Research Council. And the task is basically to be able to read these numbers, compare the number lists, left to right. There were 20 of them, 5-digit numbers, and they could be at high luminance or low luminance, and we could change the contrast as we went through that. So this is an on-axis task, and this is what we've shown in terms of what we call the plateau and escarpment of visual performance. As you increase contrast, you see that you do not do as well at 12 candelas per meter squared, a little better at 50, and at 169. Now, these have strict biophysical relationships, so this is not just empirical data, but in fact represents how the system deals with where things are in the environment. And the good thing is it's effectively binary. You want to know where it is and you want to know fast. And then what you're going to do is you're going to turn your fovea to it and you're going to determine what it is. But those are two very different things. Now, again, V lambda is a very good description of on-axis visual performance, as well as off-axis with the corrections for pre-retinal filtering, which is V10. Now, brightness is of two types. You can judge the contrast of something, how distinct is it from its background, and you can make an overall assessment of the scene. Now, what you see from these curves, V lambda still does very well for on-axis contrast judgments, but look at how different our perception of brightness is. It's very much S-cone dominated response, and that S-cone response actually grows. The brighter, the more flux that enters the eye, the more the S-cone plays a role. Now, to my knowledge, no one has a light meter that measures that. And that becomes critical because you've seen the applications when we had standards using low pressure or high pressure sodium. You now put an LED system in that replaces that has a lot of short wavelength energy. Everybody complains it's too bright. And the reason it's too bright is because our standards and light meters aren't calibrated to actually characterize how the visual system sees brightness. So let's talk about contrast first. So this is the same task that we're doing. And when you ask people the visual performance plateau and escarpment response, now this is exactly the same stimulus materials. You see this rapid rise and then a saturation. If you ask them to judge contrast, we're a pretty good linear response mechanism. If you change contrast by 10%, we perceive with the what channel a 10% change. The where channel, being able to find where I have to make those comparisons, has this basically binary response. You either see it or you don't. But contrast judgment is very different. So our applications, let's say, got lucky when we had V lambda. V lambda was a very powerful rectifying variable, but it's not very good when it comes to judging the brightness of this room, which is heavily dominated by the S-cone input. So this is a scale model experiment of a residence where you can see the subjects put their chin in a chin rest, and they're asked to make brightness judgments of how this particular space looks. So you have a warm source and you have a cool source. You have a low illuminance and you have a high luminance. These are photopic illuminants, and the reflectances are 70%. Now what you see is when you look at the subjective judgments, yes, as you increase the illuminance in the space, your perception of brightness increases, as it should. But what you notice is the 6500 of the cool source is always judged brighter than the 2700 for the same photopic illuminance. And that's also true if I simply change the reflectance of the background. Again, as you would expect, the brightness goes down, but you still see this disparity. When you apply that function that I showed you before with that S-cone, you can take those data and rectify them into a single function that relates brightness to the photopic characteristic in which you're taking the S-cone plus V lambda to characterize it. So you can actually begin to use a different way to think about how do I measure brightness. Now here's an application for outdoor. Same basic procedure. This is at the University of Washington. They want to encourage people to come to take night classes, so they wanted to know what kind of lighting should they put in. They had an existing metal halide, high pressure sodium, and LED. The metal halide was rather old, so those of you that understand that technology know it was also rather dim. And what you see is, if you plot the illuminance we measured, the high pressure sodium by a photopic illuminance was very, very high. But if you look at the metal halide, it was the lowest, and then LED was somewhere in between. Now, most lighting engineers would think that people would consider high pressure sodium to be brighter and safer than it would be, certainly for metal halide and high pressure sodium. In contrast, if you compare the brightness according to that function, it turns out, although you can't see it so well, the LED is actually perceived as brighter according to that model. And if you plot the brightness response, we drove people around in a bus, unloaded them, asked them to make judgments in 2 different directions, a bunch of questions. You see that photopic illuminance predicts, yes, it increases, but if you begin to plot it with regard to the brightness function that you have almost a perfect correlation. Getting that spectrum is right. If you want to apply roadway lighting, you want to reduce light pollution, and that I believe is our social obligation to do such things, you need to use the right measurement, the right metric to be able to characterize brightness. That way you're not over designing the brightness and you're making sure you're not underlighting it either. So we have then finally this what response is going back to Marsden's paper in 1970, which I find a remarkable paper. It was in one of the first issues of LR&T. And what you see in the heavy black line is people's perception of how bright does the light source look without glare. There was no discomfort glare. And what you see is a power function. So if you increase the luminance, your perception of brightness increases with the power of roughly 1/3. This is 0.37. The dotted lines are our contrast judgments. And what Marsden showed then was if you ask the brightness of the room, again, spectrum is constant in this case, you see that there's somewhere in between. So it looks like there are actually, as I said before, 2 distinct characteristics in that what channel. We are very good contrast judgments, of which we're using V lambda as our primary metric to characterize it, but we also, when it comes to whole field brightness, this S-cone plays a critical role. So if you're a lighting designer and you're coming up with new standards, in my opinion, just using V lambda is going to be a difficult task to actually meet that energy efficiency, and certainly for outdoor lighting to prevent overlighting. So what this all means, and I'll be pleased if you read the paper that it's included, we can't cover everything. I'd like to see lighting research, applications-based research, to rethink what it is we're actually doing. If you bring it down to V lambda, I think you're going to miss the point. So there are different channel responses at different parts of the retina that all have a different biophysical relationship to flux density on the retina. And being able as a professional to know which to apply, I think, becomes critical. And now with portable spectroradiometers that you can read on your phone with all these metrics and software from the basic SPD, you now have the tools even to make this a practical proposition. But I don't think that's it. I think that one of the things as a lighting professional, we have to think about what I said at the beginning. The what and the where are actually working together. It's a holistic system designed to, first of all, be able to tell us where things are in the environment and then to be able to interpret them. So I would like to see I'd like to see applied research begin to think about how do I characterize the luminous environment where both the where and the what are being part of my lighting design consideration. So I'm going to use this because I think it's such a good example. So here's the driving task that you have. You're driving down the roadway. This is obviously North America, not Great Britain. There's not a drunk driver in Great Britain. I want to make that clear. Forgive me for the registration, but this is intended to be a small disc that constitutes where your fovea is. If you drive down the road and you stick your thumb and you look at the back of your thumb, you include your fovea, the V lambda response, and you can happily drive down the road for quite a while without ever using your fovea. It's all a peripheral detection, because if you do the reverse experiment and you try to drive down the road looking down a narrow tube where only your fovea, you will find it so uncomfortable you can't do it for more than a second or two. And yet we have no real conscious understanding of what is so critical for the driving task. We have to know where things are, and that's what this flow information going to the periphery. It tells us we're going straight, things are going okay. If something comes into the roadway, a deer or whatever, you can react to it, and then you can apply your fovea to it to actually look and determine is it a deer or is it just leaves blowing across the roadway. So my colleague John Bullough and I published this paper a few years ago, but I think it's intended to kind of characterize what I think the kind of research we begin to think about, whether it's interior or exterior. So you have a subject sitting and doing a driving simulator, aka a video game, in which you're projecting, in this case, a metal halide source or a high-pressure sodium source. Now, off in the lower left corner is an off-axis detection target. It was a liquid crystal that we could have a back reflections. And as you're trying to drive this race course, you see that it doesn't really matter whether you have metal halide or high-pressure sodium. As you increase the luminance, you kind of get this gradual RVP, relatively flat plateau, but spectrum doesn't matter once you characterize the stimulus in terms of V lambda. But your ability to detect something coming onto the roadway is very much dependent upon spectrum. So this is a plot of the misses that they had of the targets as a function of background luminance, again measured with V lambda, and look at the distinctly increased number of errors that you're making, high pressure sodium versus metal halide. Remember, we have to think about this is a parallel processing system that I think leads us to kinds of decisions. This is, forgive me again for being a North American roadway, but this is the way we light our roads today. So we sometimes forget as lighting engineers that we actually have headlights on the roadway. I'm always surprised at that. But what you have is a fixed lighting system, and then you have an oncoming car. And what you do is you end up with low contrast. There are places where, with the headlights competing with the street lights, you drop the contrast of this child in the middle of the road. And contrast is what we should be designing for, by the way, not just illuminance. You have glare from the headlights, and you've got unknowns over here in the periphery. If you begin to rethink it and say, this is a holistic task where I have to detect targets, so I'm going to use my forward lighting system, and you notice it's an asymmetrical thing. So the target is never in full illumination. There's always a shadow behind it, which carries their own contrast with them. But you have to do something with the fixed lighting. And I'm not going to talk about the glare. I had a bunch of other slides, but I knew I was going to run out of time. And then you have fixed lighting that really is designed to do off-road lighting. Now, we're working with a lot of automobile manufacturers today, looking at how it is we can use a forward lighting system as a way of trying to enhance that. But there are degrees of freedom. We can do that with fixed lighting in combination with forward lighting. The point I want to make here is we need to start thinking about what and where we are trying to light our lighting system and get away from horizontal luminance, which has been with us since 1924. So I thank you for your attention. I apologize for the technical difficulties, but we're going to save our questions for later. Is that right, Ian? Okay. Anyway, thank you very much.